These are notes for Unit 5, Day 3, and they start on page 8 of your packet. And today we're focusing on determining intervals on which a function is increasing and decreasing. So if you think about those words, increasing means this, right, to go up in value, and decreasing means to go down in value. Our central question then is, how can I use the derivative to determine the intervals over which a function is increasing or decreasing? So think about, as a function increases, what is true about the derivative in that region? And as a function decreases, what is true about the derivative in that region or interval? We're going to try to use those derivative values, okay, so that we can make those determinations about increasing or decreasing. So let's take a look at the definition of increasing and the definition of decreasing. So we have, we let a function f be defined on an interval I, and that interval can be a closed interval, it can be all the way from negative infinity to positive infinity, it doesn't matter. Let x1 and x2 be any 2 points in the interval. If the function f increases on that interval when the derivative is positive. So you think about an increasing function going up, we've got, you know, think about derivative, I say derivative, you think slope, that is a portion of the function that has a positive slope. And so it has a positive derivative. And then decreasing, we think about a function that decreases that has negative slope or a negative derivative. So if we know the derivative values at specific locations, then we can determine whether or not the function is increasing or decreasing at that location. So what it boils down to informally is that we need to know information about the derivative values. And one way we can do that is to, if we look at question 1 here, is to give you a graph of the derivative. So this is not the function, this is the derivative, these are the derivative values. So if we think about when a function is increasing and when a function decreases, and then maybe it increases again, and then maybe it decreases again, when it switches from increasing to decreasing, that's where we found that hill or that valley, and we know those are critical points. And so we know at the critical points, the derivative is 0. And if we have a function, maybe we have a function that increases and then decreases and then increases to a point and then comes down, you know, a cusp or a corner, it still would increase. And then at that location, we'd have an undefined derivative, and then it would decrease. So it becomes important to remember how to find those critical points. So these are derivative values here in this graph. And so critical points are when the derivative values are either 0 or undefined. Okay, so let's look at the question stem here. It says the graph of f prime, the derivative of f, is shown above from -2 to 5. And what intervals is f increasing? So we know that if we want to find the intervals where f is increasing, we want to find the intervals for where the derivative is positive. Okay, so here is the derivative values, and we're going to look at these derivative values. And the first thing we're going to do is find the critical points. So the critical points, like I was saying earlier, are when the derivative is either 0 or undefined. And values for the derivative that are 0 on this graph are going to be right here. Okay, these are 0 values for the derivative of f. All of these values, anything above those locations, have positive derivative values. Anything below these locations are our negative derivative values. So as far as positive derivative values, we have positive derivative values right here, which means we have a positive derivative from -2 to 3, which is this answer right here. Okay, so so there's our positive derivative values. Now let's take a look at kind of some of these other answer options. You know, this first answer option -2 to -2 to 1 only just covers this, so that's not covering all locations. 3 to 5 are negative derivative values, so that's not correct, obviously, either. 0 to 1.5 and 3 to 5, 0 to 1.5 and 3 to 5. They're trying to get you to look at, like, you know, this these valleys for some reason. I'm not quite sure. Seems like an unnecessary distractor. This is an interesting distractor. They're having you look at this location from -2 to -1, this location from 1 to 2, and this location from 4 to 5. They're getting you to look at that location where we have positive slope on this graph to misinterpret the graph, basically. So E is a really big distractor, because it's for those people that don't realize they're looking at the derivative here. They think they're looking at the function, so they're grabbing the slope locations. And they do that all the time on multiple choice questions, so you gotta be really careful about that. So quick recap, since we have the derivative values graphed, we are looking for positive values, which are above the x-axis. Negative values are below the x-axis when we graph the derivative. Question 2, similar question without a calculator though. Let f be a function with the derivative given by this expression, on which of the following intervals is f decreasing. So again, really important to find those critical points so we can look between the critical points. So the first thing we're going to do then, we know that f is if we want f to be decreasing, we're looking for a negative derivative. First thing we're going to do is find those critical points. And so we're going to set the derivative equal to 0 and solve this. And when we solve this, I'm just cross multiplying here, x cubed equals 2. And then so we know we have a critical point at the cube root of 2. I'm not sure what that is specifically, but I know it's between 1 and 2. That's all you really need to know, closer to 1. But we also remember critical points are also locations where the derivative doesn't exist. So now we have to look at this derivative expression and say, are there any values for x that would make this not definable? In other words, would be a problem to be able to get a finite answer, compute an answer. And the answer is yes. We're always leery of rational expressions, right? Because denominators equal to 0 are a problem. So when we have x equal to 0 here, this becomes undefined. So our last critical, this is one of our critical points. Our other critical point is at x equals 0. So now we have to look between the critical points. So if you remember back to that last example where we graphed the derivative, we had the critical points were right on the axis. We can accomplish the same thing by just looking at our derivative number line from the previous section when we were learning how to calculate critical points. So we're going to put those critical points on a number line. So this is where the derivative is equal to 0. I mentioned it was between 1 and 2, so I'm just going to put a 0 right there. Okay, and then this is when the derivative is undefined, which is right here. So I'm just going to put a u there. So I'm not going to worry about graphing anything, but this is like the x-axis of the previous example. And so this would be like the derivative would come down and touch the x-axis here. And at this location, there would be some sort of discontinuity in the graph. Okay, so now we've got to look on either side, just like we did on the previous example, right? The previous example had a positive hump here and a positive hump here and a negative hump here. And so we could see our positives and negatives visually. We got to find our positives and our negatives in between in these intervals by plugging it into this. So we're going to pick -1 and plug it into this. And when we do that, we can see, and really we just have to determine if it's positive or negative. So I look at this, I say positive, positive, and I just stick a positive there. I don't really care what the number value is. So that's just like the hump in the previous example, right? All positive values up until this critical point. Now let's see what's going on here by sticking +1 into here. So I stick a +1 into here. We're looking at this. We got 1 minus 2, that's negative. Okay, so I stick a negative sign. That would be like a little bump going down on the graph if you wanted to try to graph it like the previous example. And then I got to test something out here, see what's happening there. And really, I mean, when we look at the answer options, if we're looking for a decreasing function, a negative derivative, this is the only answer option that fits with our graph. So we really don't need to test out here, but I'm going to anyway. I'm going to test 2. I'm going to throw 2 in there. And it looks like I got 4 minus 1. That's positive. So I know that this is my only interval where I am decreasing. So if I had to graph this like question 1 we just got done, it would look like this. And then maybe it would come to here, and then we'd have some sort of jump, and it would come to here, and we'd look like this with a negative value, with negative values, and then we'd have 0, we'd cross over right here, and then we'd have positive values again for our derivative. So the answer is D, from 0 to the cube root of 2. So let's kind of formalize what we're doing here. The last 2 examples, we had the derivative, and so we could just really solve those 2 problems without any calculus. But let's look at the whole process here. Obviously, I've mentioned it a few times. It's really important to find your critical points. We need points of 0 derivative values. Remember, those are the hills and the valleys, and undefined derivative values, the cusps and the corners, and the asymptotes and stuff like that. So we need to get those critical points. So I'm going to refer you back to page 6 for that process. And then we need, if we don't have a graph, we need to sketch that number line. Put down all the critical points on that number line so that we can start testing in between. Okay, we call that the derivative number line. And then we're going to test those points in our derivative expression. And then we're going to do some math, basically, and examine the sign of f prime. I mentioned it a little earlier. It's not really important to know the value, but we just need to make sure we can determine whether it's positive or negative. And then we make our justification by using the definition of increasing and decreasing functions. So let's take a look at this on a free response sort of type of question. What I'm doing is I'm giving you the graph just to help you have a visual. The actual question was just, the actual question stem just was this. It wasn't a graph at all. It says over what intervals of f of x, which is x cubed plus 3x squared minus 1, over what intervals is it increasing and over what intervals is it decreasing? So a quick graph here, we can see it's increasing in this interval from -infinity to -2. We can see it's decreasing from -2 to 0, right? I'm reading these values, -2 to 0. And we can see it's increasing again from 0 out to positive infinity. So from -infinity to -2, increasing, decreasing here, increasing here. And like I said, though, we don't have this, so we have to solve this algebraically. So going back to the process, the first thing we need to do is we need to find our critical points. Okay, so we know that increasing is positive derivative, we know that decreasing is negative derivative, we need this derivative. So that's simple enough. And we're going to find that derivative and find those critical points. So let's differentiate this. Remember, the critical points when the so we're finding these points right here. So the derivative here is 3x squared plus 6x. We're going to set that equal to 0. And this is going to be a reoccurring solution strategy. Okay, find the derivative, set it equal to 0, factor it, and solve it. Okay, those 4 steps you're going to do over and over and over. Okay, find the derivative, set it equal to 0, factor it, solve it. So we found the derivative, we set it equal to 0. We're going to factor this. We're going to factor out a 3x, and now we're going to solve it. So by solving it, I mean set this equal to 0, set this equal to 0, right? Because they're factor pairs. One of them's got to be 0. So when we set x plus 2 equals 0, we get the solution x minus 2. When we set 3x equals 0, we get the solution x equals 0. So at -2 and 0, -2 and 0, we have a critical point, right? We have a 0 derivative, which means we have a hill and a valley. Okay. Going back to this derivative, there are no points in that would be undefined, right? 3x squared plus 6x, any value of x will work. So we know we have no cusps or corners or asymptotes or stuff like that. And this is just a polynomial, best bet polynomials are these sort of things, right? Okay, so now we're going to set up our number line, our derivative number line. So we're going to first locate our critical points at -2 and at 0. This location is 0. I just had to write it off to the side. And now we're going to test in between. So let's take a look at f of -3. So I'm going to stick -3, into my derivative. Okay. So if you notice, I stuck it into this form of the derivative. Okay, and the reason why I did that is because it's easier to see positives and negatives when you have products. So I stick a -3 here, this outside is going to be negative. If I stick a -3 here, the inside is going to be negative. Negative times a negative is a positive. So that's how I'm working. That's how I'm working this factored form to my advantage. Now let's stick a -1. Okay, so again, if I stick -1 in for x, the outside here is going to be negative. The inside here is going to be positive, because -1 plus 2 is 1. Negative times a positive is a negative. And we can see it, this plus and this minus are coinciding with this positive slope and this negative slope. Okay, last test over here, choose 1. Stick in a +1 here into this factored form. 3 times 1, that's positive. 1 plus 2, that's positive. Positive times positive is a positive. So that corresponds to this positive slope here. Okay, so now we have to summarize. So our summarize is that f of x is increasing from -infinity to -2 and from 0 to positive infinity because the derivative is greater than 0 or because the derivative is positive. So notice we've answered the question. It's increasing. These are the intervals, and here's my justification. Because the definition of increasing is a positive derivative. And then we answer the decreasing question. It's decreasing from -2 to 0. And again, so here's the answer to the question. Here's the interval over which it's occurring. And here's my justification. Because the derivative is less than 0, the derivative is negative. And so that would be how to appropriately justify that, the answers to those questions. Okay. All right, so let's take a look at this question. Let f be the function given by, so again, you notice we're transitioning. Our first 2 questions, we had the derivative, and it was just a matter of looking at it with no calculus involved. The example, and then this question, I'm giving you the function, so I'm asking you to do some calculus, do some differentiation and algebraic solving to find critical points and stuff like that. So those are the 2 varieties of ways that we can ask you about increasing and decreasing intervals. So we have a function. Which of the following intervals is the function decreasing? So we're just being asked for decreasing. We know we're being asked for a negative derivative. So we're going through that process. Let's find the derivative. Here's the function. So our derivative is 300 minus 3x squared. We're going to set it equal to 0. I'm just going to quickly look at this derivative here. There's no fraction, so we know it's defined everywhere. So we're not going to worry about undefined derivatives, cusps, corners, asymptotes, those sort of things. Okay, so solving this, same steps, right? Get the derivative, set it equal to 0, factor, solve. So we've got the derivative, we set it equal to 0. We're going to factor this by factoring out a 3. So it's this, 100 minus x squared, and we're going to solve that. 100 minus x squared, you can continue to factor that, right? That's 10 minus x, 10 plus x. You don't have to. You could have solved it here and square rooted it, but when you continue to factor it, a lot of people, if they square root this, they're only going to get an answer of 10. You have to realize that because that's factorable, there's 2 answers, right? Because it's a quadratic, so we should have 2 zeros. And so we have a plus 10 answer and a minus 10 answer when we solve those two factors pairs. 3 is never going to be 0, so that just kind of falls out of the solution. This kind of speaks to the point of, like, if we solved this and we said x squared equals 100 and then we square root both sides, we have a plus or minus answer option, right? That's why teachers always say, well, when you square root something, you have a positive and a negative answer. It's because it's factorable, and that gives you your 2 answer options. All right, so we've got our critical points. We know our derivative is defined everywhere, so we don't need to worry about cusps and corners and undefined derivatives. So we can go right to our number line. We're going to put in a 0 here for 0 derivative at -10 and a 0 derivative at +10. My number line gets kind of cumbersome here. I do have to test outside my number lines here, so I've got to be cognizant of that, even though it kind of ends. I'm going to test -11. So f prime of -11, I'm going to go here. 3 will always be positive. If I stick in -11 right here, I get 10 minus -11. just 10 plus 11. So this is positive. And then I have negative here because 10 minus 11 is -1. So I get positive, positive, negative. Okay. Oh, I actually went back up here. I'm not quite sure. I like going back up here, but that's okay. So if I have positive, positive, negative, ends up being a negative answer. Okay. All right, let's test something in here. I bet I test 0, and I do. So if I could put 0 in for here and 0 in for here, I've got positive and positive and positive. Okay, or I could put it right up here. I got 3 times 100, basically. So that's positive. So this whole region from -10 to +10 is going to be positive. Okay. And that, that's the nice thing about when we find those critical points. Our derivative values are either positive or negative for the entire time between those critical points. And that's why those critical points are so critical, is because that we can really rely on that conclusion. And then let's try positive 11. So when I stick positive 11 here, I'm going to get a positive value, a negative value, and a positive value. So positive, negative, positive. Okay, or if we look at this other form, -11 squared is, we know it's bigger than 100. So we have a negative value here times 3. So we know we have negative over here. And with really reliable, predictable polynomials, we know they kind of do this and this and this and this, right? So we know we kind of have this positive, negative, positive pattern. All right, so decreasing. We're looking for our negative derivative, so it's out here and out here, which means it's going to be from -infinity to 10 and 10 to +infinity. Those are our locations for decreasing functions, decreasing intervals, excuse me. All right, let's take a look at this one. So this one's symbolic, right? We started out giving you the derivative, doing a little bit of math that's not calculus related to find intervals. Then we said, okay, now we're giving you the function. Now you have to do some differentiation and some algebraic solving to get those critical points, a little more analysis. And now we're transitioning to giving you a function that is symbolic. It's just, we have this function g. That's all we know about it. And so we have this function y equals g of x. It's differentiable and increasing for all real numbers. So think about the information that gets you. Differentiable, which means we're not going to run into non-differentiability problems. We're not going to have cusps and corners and stuff like that. Derivative is defined everywhere. And increasing, which means the derivative is positive for all real numbers. On what interval is the function g of x cubed minus 6x squared increasing? So in other words, I'm going to take g of x and I'm going to put in another function. So I'm going to do this composite substitution here, and that's your indication that we have a chain rule occurring when we differentiate. And so we're looking for increasing, which we know is a positive derivative. So we got to find y prime. So we have to differentiate this. So we know the chain rule says take the outer derivative times the inner derivative. Okay, so the outer derivative is g prime of x cubed minus 6x squared, right? When we take the outside derivative, we don't touch the inside stuff. And then we multiply that times the inside derivative, and that's 3x squared minus 12x. We're going to set that equal to 0. Okay, and then I've just these things are just kind of going up that we talked about, right? Differentiable means g prime exists. Increasing means it's positive. Okay, so we know that we're looking for we know that g prime is positive always, which means this portion of the derivative will always be a positive number. So really, all we have to do is look at this part of the derivative, because we'll always be multiplying it by a positive. So we're going to focus on setting this equal to 0. So again, we're not looking at the whole derivative here because we know we have a positive value out here always. And now we're in this scenario finding the critical points. So we're in that mode of factor, set equal to 0, factor and solve. So I'm going to factor out of 3x, and then I'm going to get my factor pairs, set them both equal to 0, and solve them. So when 3x is set equal to 0, it's x equals 0. When x minus 4 is set equal to 0, it's 5. So those are, so I'm going to do my, put my derivative, my 0 at 0 and at 4. And I'm going to test in. So let's test at -1. So really it boils down to sticking -1 back into just this expression, seeing if we have a positive or negative, because we're going to multiply it by a positive. So when I plug in -1, notice I'm just plugging it back into this factored form. So I've got negative times positive, that's a positive. Okay, so this is this portion of the derivative, but we have to remember we're multiplying it times a positive number out here. Okay, let's take a look in between. I'm sure I picked +1 here. So I stick a +1 in this factored form, and I get positive times negative times positive. So positive times negative is negative. And then I test 5 out here. I stick 5 into this factored form, and I get positive times positive times positive, which is positive. So where is it increasing? It's increasing here, and it's increasing here, which is from -infinity to 0 and from 4 to +infinity. So the answer would be A. So just a quick comment relating to this question. We could have changed up this question to ask where it's decreasing and focused on this middle interval, or we could have changed the stem and said, hey, g of x is differentiable and decreasing, which means this would have been a negative. And then we would have had to multiply all of this by negative each time, which would have flipped all these signs. So that's kind of some of the variations that you could see on this type of problem. So we will start class here, kind of going over the takeaways before you get into your class activities.